So in this section, we will be discussing about three-dimensional aspects, about three-dimensional elements which can be used for analyzing stresses or three-dimensional to perform a three-dimensional stress analysis. And we will be basically looking at tetrahedron element, and I will only highlight some of the important points with respect to the tetrahedron elements, and I will encourage you to go through the materials. I will provide some extra reading materials because the same method, it is the same method which we have used throughout the whole up to now, the same steps when it comes to deriving the stiffness matrix for the particular element. I will only highlight the most important aspects with respect to these three-dimensional elements. And also you can refer to how this isoparametric formulation is used to arrive or to derive this stiffness matrix for higher order elements. The focus in this 8th section would be on three-dimensional stress analysis. The motivation behind studying this section is that it is useful for performing stress analysis, especially in three dimensionals, because we know that sometimes analyzing a problem, even though it gives, it is possible to analyze a two-dimensional as well as axisymmetric problem, sometimes it is required to get more precise information when it comes to a 3D structure where a 3D analysis is required, especially when it comes to when we think of mechanical components which are subjected to high stress conditions, high fluctuating stress conditions, heavily loaded equipment, which we are especially used in automotive industry. We would like to analyze, let's say, perform a fine analysis in order to extract the level of the stress state of a certain component. So for this, we are required to model the system, develop a 3D model. So for developing a 3D mesh, we are required to use 3D elements. So in that sense, a tetrahedron is the basic three-dimensional element. And we will be looking at how this element is used to develop a shape functions and as well as stiffness matrix, and how the force matrix are developed in terms of the global coordinate system. Since you have an understanding about how it can be developed now using an isoparametric formulation method, I will not go into details. I will encourage you to read additional material and to get familiarized in this aspect. So I will highlight only the main steps of how the stiffness matrices can be developed in the global, using the global coordinate system. Before we move on to deriving the stiffness matrix for the three-dimensional tetrahedron element, let's try to, let's say, recap the important aspects with respect to three-dimensional element, especially in the case of Cartesian coordinate system. Assume that we are considering a very finite, let's say, element which is subjected to, let's say, different stress conditions. Let's define the coordinate system, and let's try to analyze the forces or the stresses acting on this based on this Cartesian coordinate system. If we consider this finite element, of course, we can assume the deformations or the displacements and x direction to be u, y direction to be v, and the displacement in z direction to be w. And the corresponding, okay, the lengths, yeah, it's important about the length which we marks. Dx is the length in x direction, dy, the y direction, and dz, the z direction. So the stresses applied on each face, the normal stresses, there are two stresses, the normal stresses and shear stresses. The normal stresses acting, which is normal to the plane, perpendicular to the plane, is given by sigma x, perpendicular to y direction is given by sigma y, perpendicular to x direction, z direction is given by sigma y, sigma z rather, sorry. The corresponding shear stresses acts on each surfaces can also be denoted. If you think of, let's say, the XY plane, there will be shear stress applied in this direction. Let's mark it here as tau XY. And of course, there will be another shear stress, tau in the Z direction. Similarly, if we think of the Y plane in this plane, we can think of shear stresses acting in YX direction, shear stresses acting in YZ direction. Similarly, the other face, we have again two segments, shear stresses acting in X direction, ZX, ZY. Okay, so I will upload a more clear picture when I upload an additional reading material. So for the moment, try to bear with me with this figure. So now, the first important thing, of course, we already know sigma X, sigma Y, and sigma Z are the normal stresses applying perpendicular to the planes, and the shear stresses are represented by tau XY, tau YX, and tau Z, and so on. From the moment of equilibrium moment, we already see that tau, we will not derive that, but we will use this function, tau XY is equal to tau YX. This is from the moment equilibrium conditions, tau ZY, and tau ZX is equal to tau XZ, right? So based on the the first thing, maybe if you can recollect, is that we can relate the strains to the corresponding displacements. The strain in the X direction can be written using the displacement in the X direction. Strains in the Y direction can be written using the displacement in along the Y direction. Strain in the Z direction similarly can be written the displacement in the Y direction when you get the partial derivative with respect to Z. All right. Where, of course, U and V and W are the displacements in the X, Y, and Z directions. Then the corresponding strains due to the shear stress can be written. So there are three terms: the shear stress in the XY plane, shear stress in the YZ plane, shear strain rather, sorry, the shear strain on XZ plane. Shear strain on the XY plane can be written as W by WY plus WV by WX, which is equal to shear strain by X plane. Similarly, I will directly write down, since we will be using this for the derivation of the stiffness matrix of the tetrahedral element. Right. So we know for shear stresses, there are only three independent shear strains which exist. So we can write the representation for stresses and strains rather in the form of column matrices. The stress matrix would be the normal stresses acting in X, Y, and Z direction. The shear stresses acting along XY plane, YZ plane, and ZX plane. This is the stress column stress matrix, and the corresponding strain matrix would be the strains applying in the X direction, the Y direction, the strain in the Z direction, the shear strain along the XY plane, shear strain along the XZ plane, YZ plane, shear strain along the ZX plane. As we know the stress and strain relationship, how is the stress and stresses related? Can you remember? We already discussed a special matrix which relates the stresses to strain. If you can recollect, for an isotropic material, we already derived and we used that the stresses are related to strains by the constitutive matrix D. So D is given by write the D matrix, it will be a symmetric matrix, but it will include the properties of the materials, such as the Young's modulus, the modulus of elasticity, plus the Poisson's ratio, 1 minus nu, 0, 0, 0, 1 minus nu, 0, 0, 0. Likewise, this will be a symmetric matrix, and I will provide this criteria. So this is the foundation for you, remember, just highlighted so that, because we will be using this when we want to derive the stiffness matrix for this tetrahedron element. So now let's focus on the evaluating for the stiffness matrix of this tetrahedral element. I like to reiterate, I will only highlight the important points. I will give the complete derivation in an additional reading material. Take your time, go through each section, do it on your own and get familiarized, because there are long equations, of course, since we have already covered through the steps, it is simply using the same number of steps and the same method for a different material. So I will only highlight the main important points and encourage you to read the additional material. So if we think of a tetrahedral element, let's write the coordinate system first. Right. So let's assume let's consider tetrahedral element. Our first step is to select an element type. Yeah. When we select an element type, it's we know that we see that there are 4 nodes. We can number the nodes. So when we are numbering the nodes, it's important to keep in mind that we number the nodes such that we don't make any mistake while calculating the volumes. So we follow a certain protocol so that we don't get negative volumes when we do the calculation. When we calculate the volume, because due to the form of numbering that we use. So we have, what we do is we number in such a way that we let's say we number the first 3 nodes such that they are numbered in the counterclockwise way. The first nodes has to be numbered using a counterclockwise formation when it is viewed from the other node. Yeah. So assume that we select, let's say, a certain node. Let's select node 4. Let's say because it is popping out, which is closer to our view. Then we can number the other nodes 1, 2, and 3 in the counterclockwise formation. So if you use number 1 here, number 2 and number 3 can be written in this formation. When viewed from number 4, the first 3 points, number 1, number 2, and number 3 are marked in the counterclockwise formation. Why do we do that? We do it because when we calculate the volume, we don't get negative volumes. So hope you can remember, we use the same protocol or same method when we dealt with the constant strain triangular element, where we used an anti-clockwise, counterclockwise numbering method. So once we do away with the numbering, of course, this is only important in the global, when we are deriving the matrix in the global coordinate system. If we are deriving this matrix in the let's say using isoparametric formulation using the natural coordinate system, the numbering method is irrespective. It doesn't matter whether you number them in the counterclockwise or anti-clockwise direction, you would get this correct results. But here in the global coordinate system, it is important to number them in the anti-clockwise direction, especially when viewed from the last node. Right. Once we do with the numbering, then we know we have to define the displacement matrix. All right. So in this 8.2 section, let's try to write the displacement nodes, which we have to deal with. Each node has 3 degrees of freedom in the X, Y, and Z direction. So our displacement matrix would look like this: U1, V1, W1, all the way goes up to U4, V4, and W4. 8, 2, 1. Yeah. So the next, so there are 12 degrees of freedom, meaning each node has 3 degrees of freedom. 3 times 4, we have 12 degrees of freedom we have to be considered when you're deriving the, let's say, displacement function in this next step. So in the next step, we need to derive the, let's say, come up with a displacement function for describing the displacements within the element. So since we have 12 degrees of freedom, we have to use a function, which there will be, of course, 12 unknowns, which we would have to calculate before we proceed. So the function U can be described, the displacement function has to be described using the global coordinate system, that is X, Y, and Z. Here it's the same, X, Y, and Z. Here we assume certain constants, of course, A1, A2, A3, and A4. For V, let's continue from A5, A6, A7, and A8, A9, A10, A11, A12. So once we assume a displacement function, in the same manner as we followed in the previous cases, now our objective is to find these corresponding unknowns. What are the unknowns? AI terms. These AI terms are unknowns. We would like to express this in terms of the known nodal coordinates. What are the known nodal coordinates? X1, Y1, Z1, up to, let's say, X4, Y4, Z4. These are the known nodal coordinates. We'd like to use these known values in order to find these unknown AI terms. We have done this before, so I will simply write down the answers after a lot of, let's say, I will skip a lot of steps and write down the answer you would get if you do the substitution correctly. For the U function, you would get B now corresponds to the volume of the element, which will be, there will be certain factors which we need to introduce, just like in the previous cases. Alpha 1, beta 1, gamma 1, y. Of course, now there will be additional term delta 1 z times u1 plus alpha 2, beta 2, x, gamma 2, y, delta 2 z times u2, alpha 3, beta 3, x, gamma 3, y, delta z, u3, alpha 4, beta 4, gamma 4, delta 4, u4. Right. So these alphas, alpha I, beta I, and gamma I, and delta I are functions of the known coordinates x, y, and z values. X1, Y1, and Z1 up to X1, X4, Y4, and Z4 values. In order to obtain the volume, the volume can be evaluated by calculating the determinant of this matrix. Right. So, of course, you would arrive at this step when you want to evaluate the integral for the particular function, when you want to evaluate the shape functions based on the the known nodal coordinate systems. Here, we define the volume of the tetrahedron, of course, and the coefficient alpha I, beta I, gamma I, and delta I are also functions of the known nodal coordinate systems. For example, I will write it for alpha 1, and the remaining terms I will give you in, let's say, in the material which I will be providing. You can see how they look like. So alpha 1 would look like this, the matrix x2, y2, z2, x3, y3, z3. Similarly, beta 1. So you see, you may able to find a pattern, yeah, like in the previous cases. Now gamma is a function of, let's say, yeah, x and z coordinate systems, and delta is again corresponds to only x and y coordinate systems, coordinate values. Likewise, from alpha 1 to alpha 4 and beta 1 to beta 4, gamma 1 to gamma 4, and delta 1 to 4, you can obtain the matrices. I will provide these equations because it takes a lot of time to write this on the screen. So assume that you are done with these values. The next step is then you will have to, since you have already found the shape functions with respect to the nodal coordinate system, simply rewriting or expressing these displacements with the respect with using the shape functions. So let's say the displacements u, v, and w now can be expressed as a function of, take out the variables, displacements at node 1 up to node 4, and this is a matrix which includes the shape functions, or which we use the shape functions to describe the relations, where the shape functions are given by this set of equations. So I will simply write only the shape function for n1. Likewise, you would have m2 up to n4. There will be 4 shape functions of which you can define, and you can define the shape function matrix. Yeah. So you can see alpha, beta, and gamma, delta. These are all known based on the nodal coordinates of the material, of the element. So the next step is, after we define the shape functions, we define the stress-strain relationships. We know the strains are related to the displacements via the B matrix, the so-called B matrix, again a function of the nodal coordinates. And this B matrix can be evaluated by, of course, we already saw it's a function of B matrix can be separated into submatrices, and these are again functions of alpha and beta values, which you can see, which is I will provide you in the reading material where you can go through. So this is what I'm trying to reiterate is the same protocol. Yeah, this is nothing new. We try to find the B matrix based on the nodal coordinate systems. Then we already saw that the stresses are related via to strains by the constitutive matrix. So when we think of deriving the stiffness matrix for a tetrahedral element, we need to perform this multiplication, which includes the B matrix, the constitutive matrix multiplied by the B matrix, and this is now a volume integral because it's a 3-dimensional element which has to be completed over the total volume. Here, because both B and D matrices are constants, of course, because they are either defined using material properties or geometrical properties or the nodal coordinate system, we can simply write down, since these were constants, the stiffness matrix for the tetrahedral element can be simplified to this form. So here again, V is the volume of the element, and of course the element stiffness now has The rank of 12 by tau is in the order of 12 by 12. So this is the main thing that I wanted to highlight today. What I will do now is I will after the lecture, I will provide some additional reading material to provide you the complete derivation in detailed derivation for this tetrahedral element, and also provide you a worked out example so that you can directly compare the results which you would get in simply finding, let's say, the stiffness matrix by using the equations which we have derived, or which we have used, which we have I have shown here for a tetrahedral element. And hopefully in the next session, I'm planning to start just to brief you about how the isomeric method can be applied again for this, let's say, linear hexahedral element. We will not go into details because it's since we have already gone through different types of elements, you are already familiar with the system as to how these things are derived. It's simply a matter of applying this method to a different element where we will not be able to gain additional insight. So I will just briefly mention the important points, and let's move on to discuss, let's say, thermal problems, or to discuss more about how we can tackle thermal stresses or thermal heat transfer problems, how we can model heat transfer problems using the finite element method. And of course, during the lab classes, you will be now applying this method. You will be using tackling problems where you will be solving, of course, three-dimensional problems, three-dimensional stress analysis problem, and you are required to analyze principal stresses, the von Mises stresses, and provide a solution, or given discuss whether a material will be able to withstand certain stress conditions, or if it is to withstand certain stress conditions, what are the modifications you propose. Such things will be tested in the lab classes. You can expect a three-dimensional analysis problem also during the lab classes. I know you have already worked out. We will also be looking at, let's say, afterwards, heat transfer problems in the coming lab classes. Of course, there's a lot of reading to be done on your own, but I assure you it's quite easy because we have already gone through this method over and over again. So it's simply applying to another material or another element. Yeah, and we always try to increase in dimension. And when we increase in dimensions, the number of degrees of freedom increases, the complexity of the equations or the matrices increases. We see we are at a level that these are not possible anymore using a hand calculation. So we have to use a computer in order to solve these three-dimensional problems, as well as even a simple 3D dimensional problem. It's not possible to tackle with a simple hand calculation.